So once we do this, we find out that this appears to be the best option available in terms of a sustained combustion, giving me the desired level of efficiencies. I can model this particular in the form of a CFD. I can calculate and estimate how the introduced air is getting distributed within that particular bed of fuel, whether each bed particle of fuel is getting sufficient quantity of air for its complete combustion or not, and if it is getting sufficient quantity, then the combustion should be complete. So I'll be in a position to estimate without fuel what is the distribution, with fuel what is the distribution. You see how these jets are coming out of the secondary air, and this is actually photograph of the newly developed stove where you see a completely blue flame. Let me just go back, and you see the type of combustion. This is having wood being combusted, and the type of flames which you get here are exactly the same as the flame which you get in your gas flame, in your gas burner. What it clearly indicates, the combustion process is efficiently carried out and can be carried out using the parameters which we have already discussed. We know which parameters are responsible, we know how to arrange these fuel, we know how to supply air, we know how to light it, and the process can be continued further. Going back here, what happens is, because of the type of biomass fuel, there is a lot of corrosion, because the temperature here are in the range of about 1100 to 1200 degrees centigrade. Now if these temperatures are high, then it also going to add to the corrosion. So if you have any metallic elements or any metal combustion chamber, it gets corroded in no time. I can't have a stove which needs to be replaced every 2 months. So we have now developed a ceramic stove. The inside part is a ceramic. There are 2 ceramic cylinders, an inner gap which allows the secondary air to get heated up. The inner cylinder is a conducting type, outer cylinder is an insulating type, so no losses of heat to the surrounding, and you are able to get efficiencies of this particular stove in the range of 55 to 60%, which is unheard of as far as any solid fuel burning stoves are concerned. Right. So these are the conclusions of the first part. I have got a stove now. What do I have to do? I have to combine that stove with a cooker, because ultimately I am not just interested in combusting fuel. I need to utilize the energy associated with that combustion for cooking purposes. So how can I design now an efficient cooker? This is the 4 parameters which you need to adjust. Flame to base ratio, early shut-off of the heat supply, reduction in heat losses to the surroundings, and multiple effective apparatus. You can combine these and come out with the design of a cooker. Now many of you must have used a pressure cooker, correct? How many whistles you allow to go in a pressure cooker if you are interested in cooking dal? 3. And only if I want to cook rice, 1. Right? Why whistle? It is not a whistle cooker, it's a pressure cooker. Every whistle you allow to go, you are losing 10% thermal efficiency. All the steam and energy associated with it is wasted to the atmosphere. Ideal operation to be carried out using the pressure cooker, because it is a pressure cooker, the moment you start seeing the whistle dancing, you minimize the flame flow rate. Don't allow the steam which is generated to escape. You minimize the flow rate, keep that particular gas flow rate for the same period for which you had required earlier to have 1 or 2 or 3 whistles. After which you can switch off the gas. Do not open it. Let the pressure subside on its own. Don't just open the whistle and let the steam escape. And you will get perfectly cooked meal, and you will be saving more than 50% of the energy which you would use otherwise. What have I told you? This is all chemical engineering. So one needs to look at everything in terms of what we have learned and how we can apply it. So you can combine these basic principles in this and this cooking. We have also developed a cooker where rice, dal and everything comes from one end. Hot water comes in, at the other end you get a ready-made cooked meal, right? Rice or dal and khichdi. You can prepare this particular material on a continuous basis. We have got one cooker which is capable of cooking 300 kgs per hour of rice, 300 kgs per hour, right, which is equivalent to approximately 1,000 people being fed per hour basis in terms of the total quantity of rice which you use. Again, chemical engineering. What information I need? I need a residence time distribution of this solid. Whether the time which is required for cooking of each grain can be matched if I measure the residence time distribution of the solid material, residence time distribution of the liquid water which is used for cooking purposes, all chemical engineering again. And I am addressing the basic principles which you are going to learn or which you have already learned in your second and third year of chemical engineering courses. This is just tell me how effective it is. The payback period for such an operation is less than 7 months. Even in the case of eco cooker, 6 to 7 months is the payback period. So you might be spending one go, but the quantum of fuel saving which you have will pay that money back to you in 6 to 7 months. Of course, you can develop solar dryers where the drying rate kinetics can be estimated or drying rate curve can be estimated. Simple device, again a chimney effect. Hot air allowed to pass through, I have the material to be dried out here, and these are the spinach or coriander, ladyfingers, and these are the dried. The basic difference which you see here, this is completely dry and can crumble it, but it has not lost its color because it is not directly exposed to the UV radiations of the sun. And because it is not exposed to UV radiations of the sun, you do not get discoloration and you retain the color of the leafy vegetables as such. Right? This is again another solar steam generation. This steam is being used for vapor phase, vapor absorption, refrigeration system, and currently we have 2 labs in ICT where these labs are air conditioned using solar energy or steam produced by using solar energy. You have plenty of space out here. Come up with something, harness solar energy, either in the form of solar photovoltaic, solar dryer or solar thermal. You have plenty of opportunities available in this particular area. Nainital has yesterday only commissioned the largest telescope, optical telescope. So effectively it tells you that the atmosphere is clear, solar radiations are intense, so you can harness this solar energy for these operations quite easily. Let us turn our attention slowly to biochar production from pyrolysis of biogas. What do I have here? If I mix, see, older practices where after the crop is harvested, you still have stubs which are on the earth. Many a times the general farmer, what he does or he or she does, is burns this particular material, right? You have carbon, and then you do the plowing part of it so that carbon is then trapped inside the soil. Now this trapped carbon inside the soil has huge implications and applications. One, if you have about 0.1 to 0.5% carbon in the soil, it retains the soil's water retention capacity by 50%. It improves the germination of seed significantly, almost by 80% or so. And the growth rate of the biomass, because the char still contains the micronutrients which are present originally in the soil, originally in the crop, and these micronutrients are essentially recycled. So if I do a pyrolysis of biomass, I get gas which I use for burning for cooking purposes. The liquid which I get, I can use that liquid, which are mostly carboxylic acids. I can use that particular liquid, acetic, formic acid, for recovery of chemicals. And the char which I get, I can grind and remix this particular char with the soil to improve the productivity of the soil. And indeed this is possible, and I'll show you some typical examples of this. This is a typical experimental setup, a reactor which can be operated in the temperature range of 30 to 600 degrees centigrade. This is the larger version of this particular setup, and you see the gas which has been collected from here is utilized for burning of for lighting the burners, the gas burners, and this gas burner with 20 kgs of wood will withstand for about, that's okay, thank you, 20 kgs of wood will produce gas which will allow you to sustain the combustion of burner for 90 minutes. And you are combusting on an average 10 grams per minute of gas. So you can calculate out of 20 kgs how much of gas quantity is available. 3 burners running simultaneously for a period of 90 minutes. Each burner is consuming 10 grams per minute of gas, and you can calculate how much of 20 kgs of wood by pyrolysis process is capable of converting it into a fuel which can be readily utilized. Now, if you can think in terms of a community based, where the people from a nearby locality just collect the biomass and bring it to your pyrolyzer, you pyrolyze it and supply the gas like you are supplying the biogas to a community. You collect all the liquid and supply that liquid to a chemical factory which does the distillation, extraction, and recovers all these carboxylic acids. If not, you can burn that as well. And the remaining char can be redistributed back to the farmers to be ground and premixed with their soil so that it improves the productivity of the soil. Now, such type of community-based mechanisms or community-based devices are indeed possible to prevent the erosion and loss in fertility of the soil. Another thing can be done. What you are getting here is essentially an activated carbon at the end of the operation, correct? Now, this activated carbon has a very high adsorption capacity. You can preload certain micronutrients depending upon the type of crop which you are going to take, and then premix that, and it acts like a slow release drug or a slow release fertilizer. Right? So if I add just urea in the form of urea pellets or urea balls, and first water comes, that is going to wash off most of the urea, and then not much urea is going to be available. However, if I take that urea, load it on this particular biochar and add that biochar will hold on to this particular urea and slowly release it. So like I said, it's like a extended release drug or an extended release fertilizer, which results into a substantial improvement. Again, you can model the same way. You can write down the reaction kinetics, again chemical engineering, what you have already learned. Right? These are the model validations, again the simulations and comparison with the experiments. This just tells you as the temperature of pyrolysis increases, the gas component increases, the liquid component increases, and the solid remaining residue keeps on decreasing. This is just to establish the material balance. Starting with X kgs of wood, whether I have been able to account for the total quantum of the materials which are coming out. Gases, liquid product, solid residue, whether it is weight gain or not, and you see within 1% I am able to match the material balance. These are the typical composition of the gases which are coming out: hydrogen, carbon monoxide, methane, carbon dioxide, ethane, butane, propane. All these, depending upon the operating conditions of this, can be judged. This is a typical distribution which you get when you carry out the pyrolysis, and this shows you how much phenolic compounds are there, how much alcohols are there, how much aldehydes, ketones and acids, and the water quantity which is remaining there, because ultimately biomass is also having H. Now that H, when combust, is going to produce H2O, and that water is also going to get collected. Right? So let me just see, these are the characteristics of the biochar in terms of its surface acidity, surface basicity, electrical conductivity, surface area.